In this video, we're going to talk about 8.2.2, which is repeated eigenvalues. It's not a completely accurate description of everything we're going to talk about in these problems because some of the time we'll have one eigenvalue that produces two different eigenvectors. That's when you end up with two or more rows of zeros. When you go back and solve the matrix with your eigenvalue put in, and that's a different scenario than when you have a eigenvalue with a multiplicity of two or more. And that feels more like what we had in our homogeneous differential equations in the past. But let's go ahead and let's just start with number 21. We're going to have a mix of the two types of problems here, and I'll talk you through the techniques as we get to the problems that require them. So the first problem starts off as dx dt equals 3x minus y and dy dt is equal to 9x minus 3y. And so that gives us a system of differential equations that can be written in matrix form as x prime is equal to 3, -1, 9, -3 times matrix x here. And then that gives us a determinant characteristic equation to solve here, like so. And this will be equal to 0. So this is -9 minus 3 lambda plus 3 lambda is 0. Then that's plus lambda squared, and then minus a -9 is plus 9. So that equals to lambda squared, and that equals to 0. So we just have one lambda. We don't need to call it lambda 1. Lambda is equal to 0 with a multiplicity of 2. So this is that second type, and more like what we talked about earlier in differential equations, where we have a multiplicity of 2 or higher. So we're going to solve this equation here. We're going to put 0 in. This makes 3, -1, 9, -3. Augment this with the 0 matrix, and this comes out to be 3, -1, 0, 0, 0, 0. So that means that K2 is equal to 3K1. I'm going to call K1 T, and that makes this 3T. So my matrix K that I'm interested in here is the eigenvector 1, 3. Now, because there's a repeated root, I'm going to have to solve this equation again, but instead of putting the 0 matrix on the right-hand side, I'm going to have to put K on the right-hand side, and this is going to give me a matrix P. So 3, -1, 9, -3, and then I'm going to put 1, 3 over here, and we're going to RREF that, and that gives me 1, -1/3, 1/3, 0, 0, 0. So that tells me that P1 minus 1/3 P2 is equal to 1/3. And that gives me, if I let let's see, P1 be 2/3 and P2 be 1, then I could come out with 1/3 over here. It's just as easy to make this 0 and this -1. There's lots of right answers to this. So any one answer will do. I'm gonna go with the one that the book used of 1, 2 for P. So they're saying that 1 minus 2/3 is equal to 1/3 because they just wanted to get integer values here. So, but you could have lots of right answers for what matrix P is. Just be aware of that. So then capital X, my solution here, is going to be C1, and then we're going to take K, E to the, and then this is going to be lambda T, but that's to the 0 power, so I don't need that. And then plus C2, and then we're going to open a bracket because there's going to be parentheses and parentheses. And I'm going to take K again. And this is going to be times TE to the lambda T. So this is T times 1. So that's just T plus, and then P. And then that would be E to the lambda T, but that's E to the 0. So that's just that there. So there we go. That's our first one. Hopefully that's a nice warm up for what we're going to be doing. Let's go ahead and look at number 23 next. And we're just given x prime is equal to -1, 3, -3, 5x. So my characteristic equation will be -1 minus lambda, 3, -3, 5 minus lambda is going to be equal to -5 plus lambda minus 5 lambda is -4 lambda plus lambda squared, and then we have minus a -9 is +9 equals 0. So that's lambda squared minus 4 lambda plus 4 equals 0. This is lambda minus 2 squared equals 0. So lambda equals 2 with a multiplicity of 2. That gives me -1 minus 2 is a -3. Then we have 3, -3, 5 minus 2 is 3, 0, 0. That's going to turn into 1, -1, 0, 0, 0, 0. Just multiplying this top equation through by -1/3 to simplify it a little bit. And this is the exact same row, same coefficients as row 1. So they add, they subtract to give me zeros down here. This tells me that K1 is equal to K2, letting either one of them, I'll say K2 equals T, then K1 also equals T, and I'll have a K of 1, 1. So now I need to solve for P since there's a multiplicity of 2. So I'm going to, this is to solve for K, this is to solve for P, -3, 3, -3, 3, 1, 1. And so again, I'm going to get a row of zeros down here. But this is going to be 1, -1, -1/3 this time. And so that gives me the equation that P1 minus P2 is equal to 1/3. So easy thing to do here is to let P2 be equal to 0 when there's subtraction like this, and let matrix P be negative 1/3, 0, like that. And then we're going to solve x equals C1 times 1, 1, e to the 2t plus, and then C2 on the outside of our brackets. Then we're going to go back to k t e to the lambda t plus p e to the lambda t, like so. All right, let's look at number 25 now. And 25 is dx dt equals 3x minus y minus z. Dy dt is equal to x plus y minus z, and dz dt is equal to x minus y plus z. So x prime is equal to 3, negative 1, negative 1, 1, 1, negative 1, 1, negative 1, 1 times capital X, and characteristic equation 3 minus lambda, negative 1, negative 1, 1, 1 minus lambda, negative 1, 1, negative 1, 1 minus lambda. Now, because this is a 3 by 3, we're going to have to pick a row or column to expand on. I have chosen to expand on column 1, and that makes 3 minus lambda times the determinant of 1 minus lambda, negative 1, negative 1, 1 minus lambda, and then minus this 1. Then that leaves me with negative 1, negative 1, negative 1, 1 minus lambda, and then slide this over a little. Plus 1, and then the determinant there is going to be negative 1, negative 1, 1 minus lambda, negative 1. Sorry, I'm squeezing that in there, but it'll get better in just a second. So this is 3 minus lambda times, and then this is 1 minus 2 lambda plus lambda squared, minus 1, minus, and then this is negative 1 plus lambda, minus 1, and then this is plus, and then this is 1 minus a negative 1 minus lambda, so that's plus 1 minus lambda. This is all equals 0, equals 0. So this is 3 minus lambda times lambda squared minus 2 lambda minus lambda minus 2 plus, let's pull that out as a minus lambda minus 2. So I see, and I'm going to pull out the lambda here, and I'm going to pull out the negative 1 there. So it's negative lambda times lambda minus 3 times lambda minus 2. There's minus 2 lambda minus 2 here. So I move this up. This is going to be lambda minus 2 as a common factor. Then I have a negative lambda squared plus 3 lambda here, and then minus 2 there. So that's going to factor that negative out. I'll just leave that out there actually. Negative lambda minus 2, just multiply this in there is lambda squared minus 3 lambda minus 2. That works. And then that equals to 0. So this is negative lambda minus 2 times lambda. It should be a plus 2. Or did I mess up on my sign? So 1 plus 1 minus lambda is negative lambda. So that's minus 2. Right, and when I pull out a negative lambda minus 2 from here, that changes to a plus 2. That's right. So this is lambda minus 1 and a lambda minus 2. So that gives me a negative lambda minus 1 times lambda minus 2 quantity squared. That gives me a lambda 1 of 1, and a lambda 2 of 2 with a multiplicity of 2. So let's go ahead now and leave myself where I can see this. In this case here, I have 3 minus 1 is 2, negative 1, negative 1, 1, 0, negative 1, 1, negative 1, 0. Augment that. Let's RREF it. And we're going to get 1, 0, negative 1, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. So that tells me that K1 is equal to K3, and K2 is also equal to K3, and K3 is equal to T. So this is T and this is T, making my capital K, T times 1, 1, 1. So this is an eigenvector of 1, 1, 1. So ones are running together there, like so. So that's my K1. So, and then I have when lambda is 2, this is going to be 3 minus 2 is 1, negative 1, negative 1, 1, negative 1, negative 1, 1, negative 1, negative 1. So that, when I RREF it, turns into a system of 1, negative 1, negative 1, 0, 0, 0, 0, 0, 0, 0, like so. So we have K1 equals K2 plus K3. And I'm just going to pick arbitrarily here that if I let K2 be 0 and K3 be 1. That makes K1 1. Then I also have another independent situation here where I could let K2 be 1 and K3 be 0, and that would still make K1 1. So two different eigenvectors for the same eigenvalue there. And so that gives me a situation here where I want x is equal to C1 times 111 e to the t, 1t, plus C2, and then K2 e to the 2t plus C3 times K3 e to the 2t. So I had as many representations of k there as I had my multiplicity here. So let's go ahead and look at number 27. The main thing that affected how many k's I have, though, is how many rows of zeros I ended up here with. Normally, I end up with one eigenvector because I have one row of zeros. I had two eigenvectors because I ended up with two rows of zeros. It has more to do with that than it has with the multiplicity. So, but this is how you deal with that when I have multiple independent eigenvectors that can come from the same eigenvalue. Let's again look at number 27 now, which says x prime is equal to 5, -4, 0, 1, 0, 2, 0, 2, 5, and x. So we're going to come up with our characteristic equation, 5 minus lambda, -4, 0, 1, negative lambda, 2, 0, 2, 5 minus lambda, and that equals 2. And I'm going to expand on column 1. So 5 minus lambda, determinant, negative lambda, 2, 2, 5 minus lambda. Actually, let me just bring it down here. Give myself a little bit more space. Minus, and then -4, 0, 2, 5 minus lambda, and then that's plus 0, so I'm not really worried about that one. So this is 5 minus lambda times lambda squared minus 5 lambda minus 4 minus, and then this is 4 lambda minus 20 minus 0. So this is going to be negative lambda minus 5 times, and then this is lambda squared minus 5 lambda minus 4 minus 4 times lambda minus 5. So I'm going to pull out a negative lambda minus 5. When I do that, inside is lambda squared minus 5 lambda minus 4 plus 4. This is all equal to 0. this is negative lambda minus 5, and this is lambda squared minus 5 lambda. So that's negative lambda times lambda minus 5 quantity squared. So lambda 1 equals to 0, lambda 2 equals to 5 with a multiplicity of 2. That is 5, negative 4, 0, 1, 0, 2, 0, 2, 3. When I RREF that, I get 1, 0, 2, 0, 0, 1, 5 halves, 0, 0, 0, 0, 0. So my K here, K1 is negative 2, K3. K2 is negative 5 halves, K3. K3 is equal to T. This is negative 5 halves T. This is negative 2T. I'm going to let T be equal to 2, which makes this negative 5. Which makes this negative 4. So K is negative 4, negative 5, 2. It's K1. For lambda 2, we have 5 minus 5 is 0. And we have negative 4, 0, 1, negative 5, 2, 0, 2, 0. And when we RREF that, this is going to give me my K matrix. This is going to be 1, 0, 2. And 0, 1, 0, 0, and 0, 0, 0, 0. So that's my K1 equals negative 2, K3, K2 equals 0, and K3 equals T. So K2 is negative 2, 0, 1. Now I'm going to have to find my matrix P since this is repeated. So for that, that is 0, negative 4, 0, 1, negative 5, 2, 0, 2, 0, and negative 2, 0, 1. When I RREF that, I get 1, 0, 2, 0, 1, 0, 0, 0, 0. Then this is on this side 5 halves, 1 half, and 0. So P1 plus 2P3 equals 5 halves. P2 equals 1 half. P3 is a free variable. Don't worry about it. So the easiest thing to do there is to let P3 be equal to 0, and a particular P that works is if P3 is 0 and P2 is 1 half, P1 will be 5 halves. So now we can write our solution of x equals C1 K1 e to the, that was 0 t, so plus C2 K2 e to the, and then lambda here was 5, plus C3, open your brackets here, K2 t e to the lambda t plus p e to the lambda t. One more for you. That's going to be number 29. X prime equals 1, 0, 0, 2, 2, negative 1, 0, 1, 0, x. So this is 1 minus lambda, 0, 0, 2, 2 minus lambda, negative 1, 0, 1, negative lambda equals, and I'm going to expand on row 1 here. It's the easiest to expand on because that's minus 0 and then plus 0. So this is 1 minus lambda times lambda squared minus 2 lambda plus 1 is a negative lambda minus 1 times lambda minus 1 squared is a negative lambda minus 1 cubed. So this is the first time and the only example that I'm going to do where we have a multiplicity of 3. So lambda equals 1 with a multiplicity of 3. So just like we had to use k to find p, we'll then have to find p, use p to find a matrix q for our, and we'll have a much larger solution here that incorporates k, p, and q. So let's go ahead and look here at 1 minus 1 is 0, 0, 0, 2, 1, negative 1, 0, 1, negative 1. So when we REF this homogeneous system here, we get 1, 0, 0, 0, 0, 1, negative 1, 0, 0, 0, 0, 0, which tells me that K1 equals 0, K2 equals K3, K3 is equal to T, so this is equal to T, making my K equal to 0, 1, 1. Now to find my P, I need 0, 0, 0, 2, 1, negative 1, 0, 1, negative 1. And on this side goes 0, 1, 1. So then I'm going to RREF, and that gives me that this turns into 1, 0, 0, 0, and then 1, I'm sorry, 0, 1, -1, 0, and 0, 0, 0, 0. So we have, this is not 0, this is 1. And this is P1 is 0, P2 minus P3 is 1, P3 is, right. So this is P1 is 0, P2 minus P3 is 1. So P is going to be 0. And then I have 1 and 0 is the choice that I made there. So that 1 minus 0 is 1. So that's my choice for P. Use P to come up with Q. 0, 0, 0, 2, 1, -1, 0, 1, -1, and then 0, 1, 0 over here. I'm going to RREF to help me come up with Q. I come up with 1, 0, 0, 1/2, and then 0, 1, -1, 0, 0, 0, 0, 0, which is Q1 equals to 1/2, Q2 minus Q3 equals 0. Q3 is a free variable, so Q is going to be, and then I just used 1/2, and then 0 and 0 will work nicely so that 0 minus 0 is 0. So let's go ahead and set up our solution now that we have our K, P, and Q. X is equal to C1, and then K, 0, 1, 1, e to the lambda t, so it's 1t, plus C2, bracket, and then we're going to have K, t, e to the lambda t, plus p, e to the lambda t, plus C3. And now this is going to be something new to you. We're going to have K, and this is going to be 1/2 t squared. So just imagine as you're integrating and you go from the integral of a constant is t, and then the integral of t is 1/2 t squared. So this is t squared over 2. Over 2. What did I write over t? Over 2. E to the t plus, and then 0, 1, 0, t, e to the t, and then plus 1/2, 0, 0, e to the t, and that's it. I think that that's all the examples that were in that section anyways, but that's more than enough to give you an idea of what's going on here. And there's two different types of problems you can have, where either one eigenvalue gives you two eigenvectors, or one eigenvalue is repeated and you need to find not just K, but maybe P and also Q and so on. So we haven't gone anything above a multiplicity of 3 here. That's as high as the book goes, just to show you the general idea. Hopefully you get the pattern if you get anything that has a higher multiplicity than that. The book makes a note that even though we're doing these examples like this, these aren't the only cases that could come up, because we don't get all of the solutions always being independent of one another. You need to watch out for that. And there are some problems where you might, for instance, have had a repeated root with a multiplicity of 5, but you only ended up with um, three of these matrices to come out of it because you started to loop back around on yourself and get back to the same ones that you started off with, something like that. Um, so I didn't do any of those, but there are some problems like that in the book. If you get those assigned, watch out for that. But this is enough. I'm not gonna do the complex roots 8.2.3. You're just probably not going to be dealing with that a whole lot where you're interested in complex solutions to your eigenvalues. Though it's just an extension of what happened when you got complex answers in the past, and you're going to end up with answers that have sine and cosine in them. But I'll leave that to you if you want to read that and look at that. It's a little bit more than I think we want to do just because this is bonus content for a 200 level class right now. And I didn't even cover it in my 400 level class. My teacher just said, I'll leave that to you to read. We just talked about these first two cases, and then we moved on to non-homogeneous systems, which is what I'm going to do next in 8.3. And we'll only talk about the first two cases of 8.3, which are these same two cases when we get there, and we'll skip the complex eigenvalues case as well. So see you for 8.3 next time.